In this video, we're going to talk about polarity. So the first thing we have to do is define what polarity is. And polarity depends on the electronegativity differences. So a nonpolar bond, we're going to start with talking about polar and nonpolar bonds. A nonpolar bond has a difference in electronegativity that's less than 0.5. So electronegativity difference less than 0.5. For a polar bond, you have an electronegativity difference that's equal to or greater than 0.5. So electronegativity difference equal to or greater than 0.5. So what we're going to be looking at are the difference in electronegativity values for two atoms forming a bond. So we have two atoms, they formed a bond. And remember, the electronegativity is a measure of how much each atom is going to pull on those electrons. So if it's an even pull, so if there's a very small difference in electronegativities, that is considered a nonpolar bond. If there's an unequal pull, so one's going to pull more than the other, so there's a greater electronegativity difference, that's when we end up with a polar bond. So let's actually apply this to a couple of examples. So when we actually want to calculate polar, or determine whether or not something is a polar bond, we have to use the electronegativity differences. Now, your table of electronegativity values can be found on the bottom of your periodic table. So it's the bottom right-hand corner, and we're only going to be looking at nonmetals for this. So in that table are the electronegativity values for our nonmetals. Our first example is carbon and sulfur. So if I look up carbon and sulfur on my table, I can see that the electronegativity value for carbon is 2.5, and the electronegativity value for sulfur is also 2.5. So if I subtract those two numbers, 2.5 minus 2.5, I get a difference of 0, which means that this is a nonpolar bond. Carbon and sulfur have an exactly equal pull on the electrons in that bond. My second example, phosphorus and selenium, I'm going to look for those on my table here. So phosphorus has an electronegativity value of 2.1, and selenium has an electronegativity value of 2.4. So I don't want any negatives, so I'm going to do 2.4 minus 2.1, and that gets me 0.3 for my difference. This is also less than 0.5, so this is also a non-polar bond. And then finally, I have silicon and bromine. So if I look up those two values on my table, so silicon is 1.8, bromine is 2.8. So if I subtract 2.8 minus 1.8, I get a difference of exactly 1. This value is bigger than 0.5, so that makes it a polar bond. What that means is the atom with the greater electronegativity value is going to pull more on those electrons. So it's going to be an uneven distribution of the electrons. They're not going to be right in the middle of that bond. They're actually going to be pulled closer to bromine, since bromine has the greater electronegativity value. If your difference comes out to exactly 0.5, then it is also considered a polar compound. Now, we can have polar bonds. We can also have polar molecules. So if you have a molecule that has polar bonds in it, it has the potential to be a polar molecule. So we're going to look at two examples. So our two examples are going to be water and carbon tetrachloride. And determining whether or not their molecules are polar is all based on the shape. So if I look at hydrogen and oxygen on my electronegativity value, oxygen is 3.5, hydrogen is 2.1, so this has polar bonds. So the hydrogen-oxygen bond is polar. And carbon tetrachloride, carbon is 2.5, chlorine is 3.0, so that difference is exactly 0.5, so it's also polar. Now, if it has polar bonds, it doesn't necessarily mean it's going to be a polar molecule. It can be, but it's not necessarily true. So we need to actually draw the Lewis structures. So if I draw the Lewis structure for water, and I'm going to draw it with its shape in mind, water is a bent molecule. Carbon tetrachloride is a tetrahedral molecule. Okay, so if we're looking at these drawings, even though all of these bonds are polar bonds, my water, those bonds are going to be pulling unevenly on that oxygen in the middle, which makes this also a polar molecule. Now, my carbon tetrachloride, even though each individual bond is polar, it's pulling in all equal directions. So there isn't an unequal pull on that carbon in the middle. So this is a non-polar molecule. So our non-polar molecules are going to be our tetrahedral, I can't spell, our linear molecules, and our trigonal planar. So those are all of our evenly balanced shapes, molecular shapes. So in all of these shapes, there's an equal distribution of the atoms around the central atom. Our polar molecules are going to be our bent molecules and our trigonal pyramidal. Molecules can also be polar or non-polar if we have different atoms in here. So as soon as you start swapping out different elements that are going to have different electronegativity differences, then we're introducing different poles. But as long as there's the same atoms or the same element around our central atom, these are the shapes that are going to be polar and non-polar. So the whole idea of polarity is based on that idea of pulling or uneven or equally pulling on the electrons. So if we're talking about polar bonds, we're looking at one atom that has a greater pull on the electrons than another atom. If we're looking at polar molecules, we're looking at how the electrons are pulled on that central atom. So if they're pulled unevenly around the central atom, we're going to end up with a polar molecule.